So thank you, everybody. It's really an honor for me to present and to speak today and to present the work we have been doing in the division D20. What is it? It's called, the name of the division is Sources and Sinks of Atmospheric Components. So I apologize in advance for all the people who have made a wonderful work, but this work might not be covered completely by this presentation. I had to make choices, of course, and I chose to make my presentation to revolve around the notion of sources and sinks of atmospheric components. And what are we talking about? We are talking about compounds which are driving the climate and climate change, because we have to remember that climate change is mainly due to changes in atmospheric composition. At the same time, the same compounds, well, some of the compounds participating in climate changes are also threatening air quality, and some of them are also involved in ozone depletion. The emissions are multiple. Some are anthropogenic, some are natural, some are somewhere in between, natural but partly controlled by human activities. So the good questions that the public and the policymakers want us to answer is how much of the emissions are human controlled, how much is natural. So there are emission regulations. We want to know if those regulations are working or not. And we want also to know, since the climate is changing, the whole system, the Earth system is changing quite rapidly, how are these changes affecting the natural emissions? There are several approaches to source estimation. I will first tell you a bit about direct approaches. For example, if you know that trees emit volatile organic compounds, you can place a cuvette around a branch and then measure directly the compounds that you want to investigate. Or you can have a less direct but also experimental approach, and quite useful when you want to measure how much of different gases are exchanged with a forest, for example. And then you have, well, those methods are useful, but they are not sufficient to cover the whole planet and to know how much of different compounds are emitted. So you need to do some extrapolation. And that's called emission modeling. You are trying to use the flux measurements in combination with models, with algorithms, and with suitable proxies in order to derive emission maps like this one. Of course, this extrapolation is very uncertain. There are many problems with that. So the ideal method would be to combine all that with what we know from atmospheric composition measurements. By accurate measurements from ground-based, for example, or from satellite, in combination with models and in combination with those flux measurements, we should get the most comprehensive view of the emissions. So first, the direct measurements which have been performed at the Institute in collaboration with other partners in Belgium, from Ghent and from Jean-Blou. The Institute designed and made those cuvettes, branch cuvettes, and using some tubings connecting those cuvettes to an instrument which is a proton transfer mass spectrometer, this PTRMS. We try to estimate how much of volatile organic compounds are emitted by trees, and the measurement technique is called chemical ionization mass spectrometry. It is a technique which has been used a lot in the past, and for which the mass spectrometry group has a tremendous expertise. And how does it work? But basically, you have ion discharges, electrical discharges in the instrument, which ionize some water and then makes ions, which then are made to react with air from the cuvette or ambient air in a matter of microseconds. And then the product ions are moved to this part of the instrument where the compounds are separated and detected and finally quantified. So before going further with the results, I want to tell you a bit why we care about biogenic volatile organic compound emissions. Of course, you know, the forests cover a very large fraction of the globe, and in fact, it is estimated that vegetation emits much more volatile organic compounds than industrial activities and other sources. So we have to care about those. What does it do in the atmosphere? Well, we have the biosphere emits different compounds which are quite reactive, and they react in the gas phase, and depending on the photochemical conditions, they can make fine particles, aerosols. Some of those particles can become cloud condensation nuclei, which means that they play an important role for the formation and the brightness of clouds. So the aerosols are actually a key player in the aerosol in the climate system, because, I mean, mainly because of their role regarding the formation and properties of clouds. And by this way, those emissions affect the climate because they affect radiation balance and they affect the temperature. And therefore, you have a feedback loop here where more emissions mean cooler conditions and means less emissions. So in this case, we have a negative feedback. But you have also to consider the fact that ozone is made also from the reaction of volatile organic compounds in the air, at least in the presence of nitrogen oxides from anthropogenic activities. And this ozone is very bad for health. It's very bad for agricultural yields and for vegetation. But all this is extremely complex. I will come back a little bit to it later, but that's the background for why we study those compounds. So, as I said, there is a relation with climate here. We want to know how do hydrocarbon emissions depend on temperature and light. So you have this very small tree. Of course, it's very small because we want to measure its emissions in a growth room where the environmental conditions are varied in a controlled manner. You see here leaf temperature going up and down and then up again. And this is from August to early October. And you see the emissions going up and down and then remaining low despite the fact that the temperature goes up. And those oscillations here are due to the fact that during the night there is no emission or very little emission when the lights are turned off. And this is the relation between the emissions and light intensity. You have those measurements and you have different models. I will not go into the details, but those models do quite fine, but they do not represent the fact that the emissions in the afternoon are seen to be higher, somewhat higher than in the morning. And we interpret that as an effect of the history of temperature and light on the emissions. That is to say, it is not just the instantaneous light and temperature conditions which which determine the emissions, but it's also the past conditions. So it's like if the plant has to adapt in order to adapt to the prevailing environmental conditions. We see that also in the long-term evolution of the emissions. That's again, that's the daily emissions as a function of time. So those are the measurements, the daily average emissions, and again, different models, and only the model which is fitted to the measurements by assuming that there is a in influence of the past condition, the past temperature, can reproduce the measurements. On top of that, you have also another effect, which is this very clear decline in the emissions, which mean that the more you go into the seasons from summer to autumn, the emission capacity decreases. Next, we had to verify that those findings are correct in a real environment, in a real forest near Ghent. So the cuvettes and the PTRMS were transported to that location, and there were several cuvettes in that tree to investigate how the emissions varied. And I have a comparison here between the growth room and the forest. The curves are quite different because temperature and light varied in a very different manner in real world compared to the growth room. But it remains that the emissions during the afternoon were much higher than during the morning. And looking at the emission to photosynthesis flux ratio, you also see a behavior which is quite similar to what we saw in the growth room. Also, and even more interesting, we had different cuvettes at different heights in the tree. One of the branches was mostly sunlit, exposed to sun, and another one was shaded a large fraction of the time. And what we find is that there is an effect of leaf senescence, which is that's a log scale. So it's a very remarkably exponential decrease in the emission capacity, which is represented here as a function of time. But it turns out that the sunlit branch is affected sooner compared to the other branch. So it's like if the more exposed to the sun a leaf is, and the faster it ages, and in time it is less capable of emitting monoterpenes. Next, as I said, we want to move from the purely local scale to a large scale. This shows the forest in Wielsheim, a tower. That's a collaboration with a team in Jean Blou. So we use micrometeorological technique, more specifically the eddy covariance technique, to measure the flux from a large fraction of that forest. And for that, we measure the air velocity, the vertical velocity, at very high frequency. And that's a very important aspect, is that we need very fast online measurements of VOC concentration. So that's the air inlet, and then through tubings going to the base of the tower in this cabin here, where the PTRMS is installed. This technique allows the measurements of the fluxes of isoprene and monoterpenes as a function of time. I won't go much into the details. We investigated the dependence on light intensity, on temperature, and tried to go beyond that and look at the relation to the gross primary productivity, the GPP, and you see a quite nice, close to linear relationship between the emissions and the GPP for isoprene and for terpenes, but it seems to depend on the season. So again, that's like in the previous cases in the Rouse room and in the forest near Ghent, we have a decrease in the capacity, in the enzymatic activity responsible for the production of those compounds. Also, the effect of cloudiness was investigated. It was found that when you have clouds, for a given light intensity, the emissions seem to be higher than in clear sky conditions. Another compound of great interest is methanol. Contrary to the previous two compounds, isoprene and terpenes, it's more soluble in water, and probably for that reason, we don't have only emissions from the atmosphere to the atmosphere, but also a flux from the atmosphere to the plants. And that's what is seen here. You have summer of 2009 and summer of 2010. That's the diurnal cycle. That's around noon, and you have a positive flux, which means a flux to the atmosphere. And during the rest of the day, especially during the night, we have a negative flux. So that was a bit surprising to have such large negative fluxes, which on average are much more important than the positive fluxes. And that's even worse during the winter. And this was modeled and interpreted using the assumption that there is some water film on vegetation which acts as a reservoir of methanol. So during the day, the morning, the temperature goes higher and relative humidity goes lower, so you have evaporation of this water film, and then you have a flux to the atmosphere. And in the afternoon and during the night, you have accumulation of methanol in this water film. And I think that's a really important and potentially interesting and result that should be considered in the future in the models trying to describe these type of exchanges. So these measurements are continued in different landscapes because Belgium is not made only of forest. We have also crops and pasture, and this is work which will be continued. So next we have modeling. So we are doing that a lot in this division. So we try to build inventories of emissions of different compounds like isoprene and methanol using meteorological data and data on the distribution of leaves and the emission capacities, which themselves depend on the type of vegetation that you have. We investigate the whole of climate change, of land use change, the replacement of forest by crops, for example, and also the effect of solar dimming and brightening associated to changes in the aerosol loading in the atmosphere. And this shows a calculation that's between 1979 and very recently of the emissions over Canada, Europe, and Russia. And you see quite large, surprisingly large trends, upward trends over those three regions. This shows a map of the trend over Asia. That's a model result, of course, but it is partly confirmed by independent comparisons that we are doing now. That's too recent to be shown here, but we have good indication from the formaldehyde data that indeed in many of these regions from the high latitudes, the emissions are going up as a result of climate change. What happens next in the atmosphere? We have built, since quite a long time ago, a model called the IMAGES model. That was a collaboration with NCAR in the beginning, and with Guy Brasser. So we try to incorporate all the relevant processes in the model, like chemistry, transport, deposition. So we solve this type of equation called the continuity equation on a grid. So the globe is divided into boxes with different layers in the vertical and given resolution and on the horizontal. A favorite topic of research is the chemistry of biogenic volatile organic compounds, and especially isoprene, which is the most largely emitted. Its emissions are comparable to the emissions of methane. So we need to know what happens to isoprene in the atmosphere. And until a few years ago, we believed that we really got it right, and then it turned out that we were completely wrong. That was something really missing in the chemical mechanism. And then people tried to find out what it could be using laboratory measurements and theoretical studies. And then the Leuven group Joseph Peters and colleagues came up with the LIM1, well, the LIM0 first, and the LIM1 mechanism, proposing completely new chemistry. And we worked a lot with that group in order to test how those new reactions compared with laboratory measurements. And also we incorporated that in the images model in order to see the impact of this new chemistry on for example, the oxidizing capacity of the atmosphere, more specifically the concentration of the OH radicals in the boundary layers. And you see that you have up to a factor of 2 difference because of those new reactions. We are also interested in the formation of organic aerosol from monoterpenes, which are another important class of compounds. So for that, we developed, in collaboration with Leuven, huge oxidation mechanism for alpha-pinene and beta-pinene reacting with ozone, with OH, and with NO3. And this is just a small part of the entire mechanism. It's really thousands of compounds and reactions which are put together. And then we combine this with a model for the formation of aerosol, because when you oxidize compound, you add oxygens to it, and then it becomes less and less volatile, and it's more likely to stick together and form new particles or to condense on existing aerosols. So this aerosol formation module is based on state-of-the-art estimation methods for the vapor pressures and the activity coefficients, which are really the properties which you want to know in order to predict this aerosol formation correctly. Then we evaluated our model using a very, very wide range of laboratory data. I think that this model is probably by far the most extensively validated model. Of course, the model does not work very, very well sometimes, but thanks to all those comparisons, we know quite precisely where the model is going right and where the model is not doing not so right. Because such a huge model cannot be implemented completely in a global model or a regional model, we made a simplified module, a simplified mechanism, which is compared here with the explicit model on these view graphs. And then this model has been implemented in the images model to predict the concentrations of organic aerosols and then compared with different observations. Okay. So that's all for the organic volatile organic compounds, which are interesting, but that's not all that's in the atmosphere. We have, for example, taking this plot. That's not our model. That's another model. It shows which aerosol type is important in different regions. And you have oceans, you have, well, vegetation, anthropogenic, that's mostly sulfate and nitrate, and you have dust, which is a huge source, and then biomass burning. Also, the climate is not just about aerosols, it's also about gases. Like CO2 is the major player, but also methane and other compounds. So in order to verify our knowledge of those different climate components, we need really good global scale measurements of atmospheric composition. And that's, of course, satellites are the ideal, or the choice platform for doing that, but we have to remember that the satellites, each time you send a satellite in orbit, you have to verify that your retrieval of chemical compounds is correct, because that's a relatively new science, and we have to validate and also to look at the long-term time series in order to see how, for example, CO2 and methane evolve over very long periods. So for that, so Michel in the previous talk told you about already about the NDAC measurements in the UV visible. but the Institute has also a long-standing experience in the measurement of atmospheric composition using absorption spectrum measurements of solar light in the infrared. You see here some spectrum. I will not try to explain everything that's going on here because I'm not an expert. And so it tries to estimate the abundances of compounds using a spectrum like that because the compounds absorb in the infrared. So one interesting aspect of that is that it allows to target compounds which are important for the greenhouse effect, because the greenhouse is something which happens in the infrared. This is the NDAC side. This is the TCON network. So that NDAC was used to be the NDSC. The TCON is more recent and concerns more carbon compounds. So the Institute has measurement sites, especially at La Réunion, 2 sites, and then also measurements, NDAC measurements in Jungfraujoch, Uccle, Arestioa, Haute-Provence. So what this group is also doing is retrieval of different compounds using satellite measurements. Dust, as I told previously, is a very important component of, and it's a very important source of pollution in many parts of the world. This shows a brightness temperature measured by the IASB instrument on METOP, and this range of the wave number is where you can detect the presence of aerosols, because as you see here, comparing the spectrum that you get without aerosol and with aerosol at different altitudes, the effect on the brightness temperature is quite large. Those are some results. This is a vertical profile of retrieved from Yassi in this region of Africa, or off the coast of Africa. So this shows the mean altitude of the aerosol layer and the optical depth. And this is a comparison with independent MODIS data. So the next step after all those studies, which try to really get the best possible method for retrieving those dust particles, the next step will be to try to have a global picture of the aerosol distribution over a long period. Also, methane is being investigated using satellite observations, and I'm already showing some validation using TCON measurements. This is really recent, and I think it shows really a lot of promise. The FTIR data have been used in a very large number of studies, and I cannot go into detail for all of those studies. Those are just examples of the kind of things which are done. So, as I said, it concerns greenhouse gases like CH4, also I think CO2 is here, but also compounds involved in as ozone precursors like CO and formaldehyde. So they are using data from La Réunion Island, for example, in those cases, but also from a large number of stations for which data is available in order to provide characterization of the satellite performance in different parts of the world. But besides all this very important validation work, the FTIR data are also used for investigating the long-term evolution of atmospheric composition. So one question is, how is the ozone layer doing now that we know that the chlorine content is now decreasing thanks to the Montreal and London and Copenhagen protocols. And we can use FTIR data not just to determine the trends for the total column, but even for the columns in different partial layers. So this shows, for example, the tropospheric column, the upper stratospheric column, the mid-stratospheric column, and the lower stratospheric column at different sites. And what was found from this study is that the trends are completely different in different altitude ranges, and also quite different between the Arctic, which shows, well, in this case, a very fast, substantial increase in the upper stratosphere. This is in Kiruda, probably reflecting the decrease in the chlorine content in the stratosphere. But a lot of things are going on. I'm not going to try to explain all that. I would not be capable of doing that, but also climate change is playing a role, especially in the stratosphere, for explaining this, and the circulation changes and the temperature changes in the stratosphere are playing an important role. We have, this is in Jungfraujoch, we have NO2 and we have ClONO2. ClONO2 is a compound made from the combination of ClO and NO2. So its trend, which is very negative, I don't see that number here, but it's a more pronounced trend than the trend of NO2, which is shown on that figure, which, by the way, is an intercomparison of UV visible and FTIR measurements at the same site, and which shows a very nice agreement between the two methods. So we have by comparing the trends for those two compounds, we can conclude that indeed the chlorine content in the stratosphere is decreasing. In the troposphere, the data are extremely useful as well. So this is Jungfraujoch Observatory, and those are measurements, actually two types of measurements here. One is the FTIR partial column in the below 7 kilometer altitude, and the other is the in situ measurements. And actually, by filtering those data, you get those curves, and this one is the in situ CO concentration, which is decreasing much more rapidly than the FTIR data. And how is that understood? Is when you look at the difference between the two over a period going from 1997 to close to the present, and you see a kind of an increase and then a kind of decrease. And how is that understood? We believe that it's related to the influence of Asian emissions, which have been shown recently, that's another paper, to have peaked around 2005, as in this case, in this curve, and then as a result of regulations and so on, the emissions of CO started to decrease. So I find it quite fascinating that measurements at one station, but using two different techniques, is able to probe emissions so far away from that station. It's also a reminder that the problem of air pollution, because CO is a pollutant, is really a global issue, that you cannot consider just what's going on in Belgium or in Europe, but at a global scale in order to understand the trends that we see here. Next, as was told previously, today, biomass burning is a major source of pollution in the tropics, and especially in Africa. And the island of La Réunion is ideally suited to probe those emissions when the winds go in the right direction. This shows different chemical compounds. Those are different years, 2007, 10, and 11. And every year you see for all compounds, you see a maximum around the month of September or October, and this is due to biomass burning over Africa. So using that kind of information, we can obtain information actually on the emission ratios, the ratio of, for example, HCN to CO in the fire. And that's very useful to know in order to estimate the emissions of all those constituents at the global scale. So for the last part of my talk, it will be about the use of satellite observations. This has been shown before. The GUM2 formaldehyde from the formaldehyde distribution from GUM2. This is in July of 2010, and you can see the high emissions in Russia, which were due to fires, and that was the year with the huge fire of peatlands and of vegetation in Russia. And this is the model, which is quite okay, but you see, for example, an overestimation here and underestimation here, and maybe too high here. So we have developed a system which allows to derive to updated emissions. This shows the update, which is the ratio of the optimized to the a priori emissions. So that means, for example, the system increased the emissions over Russia and decreased the emissions over Amazonia. And in the case of biogenic emissions, you have, for example, this decrease over the US and over Europe. And then this shows the model results with improved emissions, and we have conducted comparisons with independent observations like the aircraft observations over the US, and what this tells is that the improved emissions lead to a better agreement with those measurements as well, which is actually a kind of confirmation, validation of the GUM2 data set. So we did that for a large number of, quite a few compounds which are observed by satellite. I will not go into the detail. This is glyoxal, which was shown already. We have also methanol emissions constrained by the observations from our colleagues at the ULB, from the IASB instrument on METOP. And in this case, you see that the model overestimates the emissions over tropical forest and tend to underestimate it at other locations like Central Asia. So our system was able to adjust the emissions in the model in order to provide the best match. And so we have in this way a quantification of the emissions which are needed to represent those measurements. Sorry. Yeah. Pollution is also a focus of our studies, the industrial pollution. This shows NO2 over Beijing, Shanghai, the Po Valley, and the US. And you have the measurements, and you have the model using constant emissions in time, and then the model using optimized emissions required, so the emissions required to provide the best match with the measurements. And those are the emissions that are needed to achieve this agreement. And those are the trend in the emissions, so of the order of 10% over China, and decrease in the emissions over Europe and over the US as a result of the regulation in the emissions. So in the case of formic acid, that's mostly a biogenic compound. We have also IASB observations of this formic acid, also from the ULB, and the model, which underestimated quite a lot the sources of formic acid. That's a long-known problem issue, and this is, so we had to invoke some unknown formic acid precursors. And this is a distribution of the emissions that we have to introduce in the model in order to get a distribution which looks similar to that one. And so we quantified the missing source of formic acid. And we also verified by comparisons with FTIR observations at those two sites, including Réunion Island, that the optimized emissions provide also a better representation of those measurements, as well as many other measurements, aircraft and in situ. And finally, this is the calculated contributions of formic acid to the total concentration of hydrogen cations. And you see that formic acid actually represents by far the largest source of acidity of the precipitation over very large regions of the globe. So with that, my conclusions, I think that I have shown that we are able to provide not only qualitative but also quantitative answers, which the public, to questions that the public and the policymakers want to ask. However, and this is very important, there are still outstanding issues remaining. We have to deal with a very, very complex system, and research should be continued. Thank you.